software, whatever the analytical your work is there, so that analytical work can be done easily by using a Matlab. That's a computational software where it can compute your analytical things much easier manner than compared with the human effort. So here once we compare, we see about the composite and the smart structure. There is a various types of the composite structures are there, like beams, plates, shells, and membranes. So each structure, once you see how we can formulate its various properties, majorly for the structural analysis perspective, what are its natural frequencies and the loss factors. We need to understand how many degrees of freedom is there particular system of the composite. So what type of the composite is that and what is its material property, whether it is orthotropic material or the isotropic case or transversal isotropic. So unless we know these cases, we can't proceed. Then we need to understand whether we have to take the plane stress condition, plane strain condition. Then what is its strains will come. It's based on, again, whether it is a which sort of the law we have taken, or whether it's a classical laminated plate theory we have taken, or the first order shear deformation theory. Am I audible to all? Hello?
Yes, sir, you are audible.
Okay, okay, thank you. So we need to understand whether it is a first order shear deformation theory or which sort of the theory we have considered for this particular analysis of a composite structure. So then we need to go for a stresses and strains relation in terms of a ABD matrices. Then that particular ABD matrices, after these stresses and strains and force equations, moment equations, and these moment and these equations, again, we have to give in a energy formulation of the energy equations. In the energy equation, from the energy equations, we can find what are the stiffness matrices and the mass matrices. And these matrices, by these totally we can't get what is a composite natural frequencies. Again, we need to convert these composite thing to a finite element formulation. This structure here, this complete structure, because composite laminate will have a various number of laminas. So these lamina stacking sequences we are combining here, and once we are combining here, then we need to convert these stresses also from the material coordinates to a global coordinates. So this transformation is also has to be done, and after that only we can convert these into energy formulations and energy equations. From the energy equations we can get the stiffness and the mass matrices, but those stiffness and the mass matrices is cannot be obtained for a natural frequencies, because we got a now structure, but structure is having a many degrees of freedom. We need to segregate that structure into a that particular laminate we have converted into a one structure, either a beam case or the plate case or the shell case. That structure completely we need to make into a different elements. So which sort of the elements we have to consider there, and once we consider that elements, and we need to find the shape functions, and these shape functions, in terms of these shape functions, the deformations only, we have to give or the derive these strain equations, and these strain equations again we need to substitute in these energy equations or in the stiffness and the mass matrix equations, and then we'll get a final one elemental stiffness and the mass matrices, and already a deformations, elemental deformation. These elemental deformations of the stiffness matrices, from these we can find what are the equations of motion, and these equations of motion we have to combine these elements into a one complete structure. Then we'll get a structure equation of motion. So then that equation of motion only we can use for the finding natural frequencies or finding these loss factors. So these are the total scenario or the total procedure we are going to follow for analyzing any composite structure. So once you take these smart structures or the smart materials, these are the microrheological elastomers or the various electrorheological fluids. They are having this G value. So once you take this G value also or the composite structure into a smart structure in between this layer. Already we have seen in the morning case, the core layer will have only the G component, also called as the shear modulus only. So these shear modulus, we have to combine in the ABD matrix. Then we have to follow the same procedure, whatever we have done for the composite. So this is a long procedure. These long procedure, we can to make these into a one Matlab or programming. It will take some months of the time to make into a one complete Matlab code for any composite structure or a one smart structure. And this will be varied, so you can refer many of morning I given the uh, papers,
Sir,
published
your
papers.
slides are not changing.
No, I am not. I am not changing.
Okay, you are not changing. Okay, fine, sir.
I am just basic introduction I'm giving
Okay,
for how we can apply the MATLAB to the composite and the smart structures.
okay.
So these procedures are there. So first, I thought, okay, it is more useful to the participants to discuss how these mathematical formulation can be derived or can be done for a various examples. I take a few example here. So those examples we'll see. And even though it is repeated in the last yesterday's session, yesterday's morning session, but to link up only, I have just added those slides to you. So that we can get ABD matrix and what are the governing differential equations and all. So after that onwards, I'll give you the new components and how we can make these mathematical formulations. And after these mathematical formulations, same mathematical formulation, we can write a MATLAB coding. And as we already see, this is a 3D elastic element. So there is a 6 faces and each opposite faces subjected to the same amount of the stress, but in the opposite direction. So then we got a x-axis, y-axis, z-axis, then x-axis perpendicular to this one, and y-axis perpendicular plane, and z-axis perpendicular plane. The opposite faces is subjected to the same amount of the stress with the opposite direction, so that these element or this element is in the static equilibrium condition. If any variation is there, then there is some elastic deformation will occur. That's what we will discuss in the strength of materials. So this is about the analysis of the linear elastic solid. So 3 equations are related to the static equilibrium equation. That's what we see in the previous case. It is static equilibrium. So that's the representation is in this form, static equilibrium equations. Then conservative or constitutive equations. These are the stress and strain or the material response equations. So alternative for the strain stress, because the stress strain both are same, either we can make it inverse. Then geometric relations, major lambda are also called the kinematic relations. There is a 6 equations. So stress and strain relations 6 equations, and here 12 equations, and 3 constitute is a static equilibrium equation. So the total combination is the 15 equations is a major role to play. Sorry, 15 equations major role to play. And here to solve these one, normally we'll use these boundary conditions to solve this particular case. Then there is some special cases are there. Mostly whatever the structures we have taken is in the come under these plane stress or the plane strain condition. So plane stress or the plane strain, that's what we see. previous session. For the geometry with the 2D plane stress and then plane strain condition, the number of stresses are reduced. And that is about the plane stress and the plane strain condition can be applied to any sort of the membrane or the structure. So these in the previous class we have considered one laminated composite plate. This plate is subject to the deformations, and these deformation here I considered, I assume this as a classical laminated plate of the beam theory. So according to this classical laminated plate of the beam theory, we got this deformation only one strain. So in the same way, we can get the first order shear deformation theory, where you can get one more element of the shear. So here there is no shear element is there, but their shear element will be combined so that your equation will be advanced. So here, what are the strains in a mid plane strains and then the top plane strain? At a particular instant, what is the strain normally we will take for the either top layer or the bottom layer. That's what we are seeing. E is equal to U naught minus ZXZ. So these are the top layer we have considered here. So if you take it this one bottom layer, then obviously there will be a positive sign will be there. So if you take normal here, we take as a negative sign because of this element. That difference, that also we have already seen. This is XZ plane. The same way YZ plane we can take, and strain equations. Once the strain equations are there, then on this plate, how the forces are being acted, that will derive with a transverse shear force per unit length, then in plane forces and moments acting on a small element. Then forces and the moments. And then we got these stress and strain equations in terms of the Q matrix. Then these are the forces and strains in the ABD matrix. So in this ABD matrix, let's say you got a one MRE or the microreactor will be combined here in the next two more elements will be added here normally. So even if you have a shear deformation theory, then your epsilon values are the first order shear deformation theory or the higher order shear deformation theory. So these can be added here. So if you want to refer those who would like to go further into these details, maybe you can refer these laminated composite plates and shells by the J.N. Reddy. So that book will explain these various number of theories very broadly and very detailedly. They will discuss all these discussion. Those who are interested, they can refer that book. And then these are the ABD matrix for a composite structure itself. If you are adding with any sandwich, then some more elements will be added here, and related strains and related forces will be added here. So then we can form a strain energy equation. From the strain energy equation, we can get a stiffness. So here, once these stiffness matrix is over, that's what the mechanical properties of the composite, whether it is tapered or the uniform parameters. I am taken here as a and external forces. If it is there, then these things as an input we have to give as input, because now we are going to make a finite element modeling. So now the discretization of this composite plate using here he took a 9-noded rectangular element. Maybe we can take a 4-noded rectangular element. What are the various noded elements are there, that we'll see again. So here he considered all this composite plate with a you can take a 3-noded element, a 4-noded element, or maybe if you want to take this as a 3-dimensional element or 2-dimensional element. So that's all your wish, and based on the requirement and the nodal connectivity. So once I already discussed like previously, you consider a composite, or the composite now has become a one plate or a shell. as a one single layer. So that layer, now we are going to divide these into a various number of elements. So normally these elements of the 2D will be for the plane stress cases, and where the plane strain condition will take for a thick objects where there is a more thickness is there. So in the thickness, normally we'll go for a three-dimensional object, or even we can go with a two-dimensional things also. So three-dimensional element also we can able to consider. And once you consider this one, each element from one element to another element, that connectivity, how it is being connected. So that is called the nodal connectivity. While connecting this one, there should be a continuity should be there. So there is a C0 continuity, C1 continuity, and the C2 continuity, or the C square continuity, whatever. These continuities are based on the what is the order we got it. So let's say we got the first order, then we will go for the C0 continuity. Let's say you got a, then second order you got a C1 continuity, the third order equations, then you'll get a C2 continuity. So like this way, the nodal connectivity elements are there. So those things just I'm revising. Those are already familiar with the finite element modeling. They are already familiar with that. But anyway, those who are not having a much touch with the finite element things, that's why I'm just briefly explaining those things. Then for that, once there is a each element is having a continuity, then for each element, now you can take here each element wise what is the stiffness matrix and the mass matrix. So how these stiffness and the mass matrix we are going to do. So this stiffness of the mass matrix, once we get the nodal connectivity, we know that each node element based on the how many number of nodes you have considered and what is its. So that we'll see now. Yeah. So we have a various elements here. Dimension 2-node bar. These are normally used for the bar elements, beam elements. So bar and the beam, there is a only degrees of freedom will be varying. So it is a two-dimensional, two-noded bar. Then a two-dimensional, three-noded triangle you can consider here. Then two-dimensional, four-node quadrilateral. Then two-dimensional, three nodes can be considered, and two-dimensional, six-noded triangle. So here the triangle we got six nodes. Then two-dimensional, eight-node quadrilateral. So these four-node quadrilateral also we can consider here one more element or the one more node here at the midpoint. So then one midpoint, if you consider here one node, then it will become nine-noded. And here you can see a three-dimensional, four-noded tetrahedral element, 10-node tetrahedral element, three-dimensional, eight-noded brick, three-dimensional, 20-node brick element. So like this way, we can elements in a finite elements. Each element will have a one how many degrees of freedom is there based on this. So I consider here only for the one four-noded element quadrilateral type. So where is a each element given a number. So these nodal elements are the nodal coordinates zeta, eta. So these zeta and eta are related with the first for this first element 1/4, 1 minus zeta and 1 minus eta. And n2 this element will have a 1/4, 1 plus zeta into 1 minus eta. And then to the third node will have a mode shape function called as n3, which is equal to 1/4, 1 plus zeta plus 1 plus eta. So n4 is fourth element, because this is the 0, 0. This will be a positive for both. Zeta and eta will be a positive and equal to 1. And whereas here, here at this element is a zeta is equal to -1, eta is also -1. Then eta, which is equal to positive 1 here, and zeta element is here. So we can consider this n4, which is equal to eta is a positive and zeta is equal to, because zeta is -1 here. So minus sign 1 by 4 zeta 1 minus zeta into 1 minus eta. So these zeta and eta elements for 4 noded element. In the same way for the 9 noded element, 8 noded element, we can find. And the similarly for the triangular element, how many are there and what are the shape functions. So whether these shape functions can be derived in the form of a, so that's what these displacements in the form of a shape functions as well as the these finite displacement. So if you represent in this form, these can be substituted in our normal equations. So that's what once the nodes, the 9 noded element of the 4 noded element or the 8 noded element, so you consider that nodal connectivity, we have to check whether this connectivity is a continuing or not. So if it is once continuity is followed, then only we can use that particular element, and if it is not there, then we need to make it the continuity. The continuity should be followed. So once the continuity has followed, then we can substitute that displacement equations into a normal or the finite element, whatever, composite, these equations. In these equations we can, here you know the u, and now you can get the epsilon x, epsilon y, gamma x ray and all. So once we substitute in the form of a shape functions, then this we can get the elemental stiffness and the mass matrices. So these elemental stiffness and mass matrices is only for that particular element. So now this particular element equation, we have to combine each element, then we can get a global stiffness and the mass matrix. Is nothing but for that structure we have got a one complete finite element formulation. So once we got stiffness and the mass matrix, we know that the natural frequency, which is equal to root of stiffness matrix by the mass matrix. So by this equation, we can get the eigenvalue problem, or the here the boundary conditions also we can apply. Then we can get the eigenvalue problem. In this eigenvalue problem, we can get the eigenvectors as well as the eigenvalues. Eigenvalues are nothing but these natural frequencies, and these mode shapes also we can draw from here. Then extract natural frequencies and the mode shapes. That's what in the normalized form. Once we get these, extract the natural frequencies and the mode shapes, then we can get the transient vibration responses of these particular. Already in the morning session we have seen this transient vibration. There is a displacement is reduced with a increasing of the magnetic field. In the same way, we are a composite element or the composite structures, you can observe its own responses. The majorly transient vibration responses also we can get. So here I took one case where there is a nano composite. Normally you are discussing about the nano composite, hybrid composite, where the nanoparticles have been added inside the matrix, and then we fabricated these composite plate, the 3 tapered configurations as well as the one uniform tapered configuration. So here you can see there is a white portion where there is a dots are there. These all are the multi-walled carbon nanotubes. So these carbon nanotubes have been added into this composite fabrication itself. So now we got a hybrid composite uniform plate, and here it is a hybrid composite with a multi-walled carbon nanotube tapered configuration, this C1 configuration and C2 configuration, and as well as the C3 configuration. These 3 configurations already we discussed in the morning. So in these we can add a composites. We added a carbon nanotube while fabrication itself. So then for this, how the mathematical or the displacement field consists of a this axial deformation. What are these displacements are there? So these displacements u, x, y, z, t, which is equal to u naught x comma y t.
Sir, we are losing your voice.
Is it clear, madam? Now?
Yes, sir.
Hello.
Hello, sir. Yes, sir. You are audible.
Okay. So these are the displacements u, v, w. The u in terms of a measure the mid plane displacement plus what is at the top or the bottom layer. Be here in this case maybe a bottom or the top based on how it is got deformed. So here they got a plus positive sign signature, or positive sign. Then z is a height of this one and psi is a here he took a first order shear deformation theory. Then epsilon x, epsilon yy, and these are the strains. Strains also in terms of the mid plane as well as z into these curvatures and gamma yz and the gamma zx, which is equal to the gamma naught. Then here sigma. Now we got the displacement equation. We know that the displacement equation, as we already discussed, for the plate case also already we got here also this plate case. We got u values and v value and w values and substituted here we got the strains. In the same way here also we got the strains. Then these terms. So now we got the strain equations. Just briefly discussing. Maybe this refer this paper you can refer. Then stress which is equal to q epsilon, as we already know, is q and epsilon, where q terms q11, q12, q21, q22, then q66 because the plane stress condition there, and q44, q55, and epsilon strains. So here it took a how many degrees of freedom? q11, q22, q12, q66, and q44, and there is a q55. These are the two external strain or the shear terms. Then sigma, this q, we got a global local to the global transformation on the composite. So for this, we got this q after this transformation. Then we got a q. That q we can substitute here the sigma, which is equal to epsilon. These are the material stress and the strain. Where this one is a global stress and the strain, and the global material matrix. So that is the q. So q after this transformation with the angle as well as the which each fly orientation. Then this angle because of the taper. So sigma epsilon. Then once you got this sigma, you know that the sigma can be converted into mx, my, mx, my, and m. The force terms in terms of epsilon, the force per unit length is nothing but a stress, and then the strains. So these relation we got in the same way we can get there. These we can substitute here stress equations, and we can get u. Then you can get the k also. The same way here we can substitute the u, ut term, kt, k, and u, m, u. So these are the both strain energy equation. This is a strain energy equation, and this is a kinetic energy equation. And the mass term for this u, and these are the moment of inertia. and the final stiffness matrix we can get ABD and A of the shear. Then again, what are these U values? These are the already we have seen. So once we get this stiffness matrix, now the finite element formulation we consider here. So this particular case where there is a tapered composite with a nano insertions. So multi-wall nano tubes inserted here. So for this case, we got the stiffness and the mass matrix also, mass matrix here, and we here it's the stiffness matrix. So two matrices we got. Then we have to apply a finite element formulation. This finite element formulation, the same procedure we have to follow here. This one is a discretization of the plate. Now he took as a 9-noded rectangular element. Then nodal connectivity after the elemental stiffness and the elemental mass matrix. Then global stiffness and the mass matrix. Eigenvalue problem. The abstract natural frequencies and the mood shape. Then transit variation. So now we are going to do the finite element formulation here. So in the finite element formulation, n is a shape functions. We got the shape functions in this one. Then the finite element equation of motion, what UE, KE, and UE and FE. So these for the elemental equation of motion. But whereas we need it for the total structure of the global equation of motion. So that will be M, U, A, U. So then once you consider this as a free vibration, this term will become 0, and then K, U double dot, then M, we can get a natural frequencies. So this is how we can get the natural frequencies of this one. So now, anybody got the doubt how we can evaluate these composite structures, mathematical formulation? Any doubts?
Sir, your voice is lost.
Any doubts till this point?
No, sir.
Anybody doubt? You can raise your hand or you can put it in the chat box.
Any doubts, people can keep it in the chat box.
Yeah, I think we can move, madam. I think.
Yes, sir.
So then, this mathematical perspective, how one example I took for only for finite element formulation of a Bernoulli beams. These Bernoulli beam, here simple beam theory we consider. Here the assumptions are the member cross section is constant and the cross section dimensions are less than the overall length. So L by T should be greater than 10. That is a Bernoulli beam condition. Then the linear variation of the stress and the strain, the small deformation. Now, as it is a beam case, we have a two nodes, and it is a y direction where W is the displacement here, and in the x direction we have a u displacement. So there is no y. So then the displacement u at the distance y of the beam middle axis. So u can be written as minus y dou w by dou x. Then strains epsilon x dou u by dou x, and which is equal to minus y dou square w by dou x square. Where gamma xl will be equal to the 0 as there is only two element and there is no shear is happening there. Then maybe a motion could be the gamma. I mean, uh, Bernoulli beam definitely will have a gamma x, where shear will be equal to the 0. So in this case, we can find these energies very easily, and the very limited number of equations will be there, where u is equal to half integration of v sigma x epsilon x dv is equal to half the sigma x, you know that e into epsilon. So epsilon x, then we squared, and then u, which is equal to half integration. So now this dv I can write in form of a dA into dx. So this dx is there, dA is area. So integration of this e a we can get as a iz. So iz dou square w by dou x square. Then we can get a dx. The external work for this element dou w, which is equal to integration of minus a to a p del w into dx. So we have the 2 degrees of freedom at each node w on the dw by dx. So these are the 2-degree freedom element. We got this element w of the deformations. Then w1, because it is the first node, w1 dw by dx, and then w2 dw2 by dx. So here it is each element is having only 2 degrees of freedom. One is the stress and another one is the displacement, and another one is the strain. So that is dw by dx. So the 2 for one element, first element w1 and dw1 by dx, and another element w2 dw2 by dx. So this is a 2 degrees of freedom. So because of there is no shear. If the shear element is there, then we will get a 1 more degrees of freedom. And the transverse displacement is interpolated by the Hermite shape function. So that's what the element WE and the shape function. The shape function here we got only the 2 elements, then n1 each 2 degrees of freedom system. Zeta only is the only one element, because we don't have the eta element. So because there is only x direction is there. So then n1 of 1 by 4 2 minus 3 zeta plus zeta square, and n2 zeta, which is equal to half 1 minus zeta square plus zeta cube, and n3 zeta, which is equal to half 2 plus 3 zeta minus zeta square, and n4 zeta in that is the function of zeta, and 1 by 4 minus 1 minus zeta plus zeta square plus zeta. So the strain energy absorbed is obtained by u, which is equal to half it in the elemental way we got it, this one. We got a kinetic energy from stiffness of the element. So here it is the potential energy or the strain energy. So right here a z by a cube and nt n. So these elements are nothing but our, so this, so up to this element we got as a stiffness. So that stiffness we substitute, and the stiffness of this particular element Ke, then the work done by the distributed forces is defined as del We. So integral minus a to a p del w dx, then p del w a d zeta. So because here only the one element is there. So from these we can get the nodal force. So this elemental force Fe, which is equal to P by 12. So 6L L square, 6L minus L square. So then we got a forces as well as the stiffness. So these elements we can directly substitute and we can get the values. Your mass element is not included, you can ask for work for this mass element. So this is one simple example I have given to you to understand how the mathematical formulations can be. So these are the various references, the dynamic characterization of CNT reinforced hybrid. So all these CNT added hybrid uniform and the non-uniform composite plates. I took from this paper by J. Lakshmipati and R. Vasudevan. Steel and composite structures, volume number 30, number 1, 2019, it got published. And the mechanics of composite materials with Matlab. So there is even a good book where you can find many codes related to the composite structures and various mathematics or the various problem solving. So by using a Matlab by George Jed Wides and then Peter I. Carton from the Springer application. And these Collar mechanics of composite structures already referred in the previous slide by LP Collar and GS Springer. And then one online course is a conservation principles in continuum mechanics by Walter E. Heisler. So these are the references I took. These are background for writing any Matlab code. You can find in the similar way, you can find many books for the finite element with Matlab coding. So they will help you to how to write the codes for a finite element models. Then whereas these mechanics of the composite materials with Matlab. So this book will help you to write a codes for the composite materials or the composite structures. But structures is not a very full-fledged book, but structures you need to write a code and you need to develop that one. So that is the major thing here. Then already in the previous slide we have included for vibrations what are the Matlab book. Raw Vidukipati is there, that is online available. So this part is related with the mathematical formulation. So once you are okay with this, then go to the Matlab course, which are related. Once a few sample Matlab course I have, I will explain to you. So how we can write a Matlab course for the composite.
Any questions from the participants can be posed? The most unresponsive crowd.
Okay, then we'll move to the Matlab. Can you able to see this Matlab code, man? Is it appearing?
So we can see the slides, not the Matlab screen.
Okay, are you able to see this one now, madam?
Yes, sir.
Okay.
Yes, sir.
So now this for the uniform laminate case, where you can get these ABD matrices. Then CLC is clear all the window and will be clear. the total that command window will be cleared, and close all, which if it is already operating, that we can use this command called close all, and clear all. So already existing any data is being running and all, it will be clear. Then in the directory also it will be clear. That format short, which means whatever the results will be there, all will come in the short form. That means only the digit 4 only will come. So after that digit, then only 4 digits will come. After the dot or the fractions, we get only the 4 digits. The display, we can select the material. We have like 6 different types of the material: graphite or epoxy, one lamina, and where these 3 angles are there. I mean 3 ply orientations are there. One laminate, then the carbon epoxy 0 and plus or minus, so 90. Yes, there is a 8 elements are there, 8 plies are there. Then graphite, so maybe it will consider as a, then boron, glass epoxy, and the new material. So we can enter here like this way. We can, it will be displayed to the output. Then mechanical properties of graphite or the epoxy lamina. So these are the taken as a reference things, or the reference thing. E1 is the Young's modulus in a normal one direction, or the first x, maybe x or y you can take. That's all your wish. And maybe T2 can be taken as a y direction, and the nu 1 2 and G1 2. The nu is the Poisson's ratio, and again the shear strength, and theta value, how many number of degrees of freedom, and theta angles, and nx, ny, and nxy. So then this compression, and then the tension, what are these? Sigma are the stress values, stress and the in the tension is in the second direction. In the first direction, or the x direction, we can say is how much is the stress, tension, and compressive stress. And then in the second direction, tension and the compression, and this is about the shear one. Then the same thing else too. So these for the carbon epoxy. First one is the graphite epoxy, carbon epoxy. Same way we got it. And then choice 3 for the graphite epoxy. Then we got what is the displacement, n is the input, enter the number of layers and total numbers, and theta value, displaying this thing. Then for these, what are the values are available, either then fourth to element, what are the elements and what are the input values, total number of layers, because 3 and 4 we have not given the how many number of layers and all we have not given, because here we have given the number of layers and there we have not given. That's why we can give this graphite epoxy as a number of layers, how we can give. So that way also you can write. Then is the graphite epoxy, then about the boron epoxy. Then here what is input value of the normal force per unit length and in the x direction, and normal force for the unit length in the y direction, and enter the value of the bending moment per unit length in the x direction. Then enter the value of a bending moment per unit length in the y direction. Then enter the value of a twisting moment per the unit length. So then choice 5 will be the properties of glass or the epoxy. So for this, how we can give these inputs, and else the finally a new material where you can give all the properties by yourself. So like this way, whatever the element you have considered, so for that element we can do it. So here even in terms of it, like we can take a fiber and as well as the matrix values and the volumes. So according to these, we can find out the fiber direction and the Young's modulus of this matrix. Then we can find this Young's modulus, fiber Young's modulus, and even in the first direction after the fiber one, you know, this E1, this F and M are related with the fiber properties. So here the fiber property, fiber Young's modulus, and matrix Young's modulus, and the fibers volume fraction and matrix volume fraction. And these the fiber Young's modulus into the not eigenvalue, this is the Poisson's ratio, and mu f and mu f, and the T is the thickness of the fiber and thickness of the matrix. So then EF and the VF plus EM into VM. By this we can find what is the composite, I mean already final composites in the first direction, the X direction, what is the Young's modulus, and the composite Y direction, U2. Then nu12, this is what is the Poisson's ratio of the composite layer, and GF is the shear modulus of the fiber, and then the GM is the shear modulus of the matrix. Then G12 will give us the total modulus or the shear modulus of a composite structure, whether it is a plate or normally it is a laminate. So N is the input, enter the number of layers. Now we got one lamina property we got. Then we can get a number of how many number of layers are the total number, and a number of stacking sequences, and after that the theta value, because we had to convert these into a nx. There is a normal force per unit length, then n by moment, and then the stresses, the tension and the compression. You can enter a ultimate shear stress. So nu21, nu12, E2 by E1. So then we can find that is what is Q11, Q12, Q22, Q16, Q26, and Q66. There is a, as you already know, this is a plane stress condition. Then H theta into N 0, 1 comma N plus 1. Then we can find out the ABD matrix here. K to N, how many number of layers are there here? So based on this number of layers, we got this cos theta and sin theta, this theta conversion. Then now it is the orientation. Orientation will make all the orientations into the one side, and then after that, here there is no tapered case. That's why it's only the one transformation, cos theta and sin theta will be there. AA, BB, DD. Then A which is equal to A plus AA, B which is equal to B plus BB, and D which is equal to D plus DD. So then we got all the Q matrix as well as the Q bar term, and then Q bar term we converted into a Q for with this transformation. Then ABD matrix. Then here this Q bar has become Q bar bar. Now, then we got a ABD matrix. So that's how we can get the ABD matrix for a composite, any composite structure. Then what is about here is the mid surface strains, then global strains. Then we converting these strains also, and here actually we majorly this written for the failures actually, as we are not discussed these failures. I am not going to discuss this one, but whereas up to this ABD matrix, still finding the ABD matrix is the most. This is how we can write your own code. So for whatever the problem you are going to take, and then on which one you are performing the experiment. So based on these values will be changing. This I have given you a short idea or the brief idea how we can write a coding or Matlab coding for the composite structures like ABD matrix. Once you got it, then you can write for the energy equations also. Then energy equation, then finite element formulation. Then after that we can write for the K and E for a elemental matrix. Then once the elemental matrix is over, then you can write for the total structure. Then you can find the natural frequencies and the shear modulus. Sorry, you can find the loss factor also. And then even transverse deformations or the transverse responses also you can note it down. So like this how I think my session is useful to you to make you some basic understanding and to start your research work in the composite materials, in the composite material, and where you can able to combine your MATLAB abilities also here. And those who want to work majorly, they can take various books, and then already I referred you good books, and these books you can refer and you can practice. Then definitely you can also publish a good publications or good papers in this area, and they can solve various problems in this area. So with these, any doubts? Hello, till now?
Any doubts with the participants? No doubts, Tirupati sir.
Oh, thank you, sir. Paramassivam, sir. REC.
Participants can unmute themselves. You can unmute now. You can unmute and give the feedback.
Thank you, sir. Those who are having doubts, definitely they can raise me. Not only now, after that also you can raise to this mail ID.
Sir, good afternoon, sir.
Good afternoon, sir.
Sir, shall I ask one question, sir? Very nice presentation, sir. Clearly explained.
Definitely, sir.
Okay, sir, can we do metal matrix composite in this way, sir? Particulate metal matrix composite, sir.
Particulate one. No, I am talking about only the fiber one.
Can we do an, sir?
Achapati, problem.
Metal matrix composite. Is it possible? Can we do, sir, like this?
No. Actually, only you will get the problem in the how you are converting these ABD. There only you will get a issue, and whether it is a particulate composite or a fiber composite, because I am discussing about fiber composite.
Yes, sir. Yes, sir. Thank you.
So you are asking about the particulate or the fiber?
Yes, metal matrix composite, particulate metal matrix composite.
Then particulate means you are like you have to go with another one. Yeah, that means fiber will be a small particles, is it?
Yes, sir. Yes, sir.
Fiber won't be a long, so you'll be having a short fibers, is it, sir?
Yes, sir. Yes, sir. Yes, sir. Correct, sir.
So in that case, what you can do is you can make a specimens. There is a ASTM standards are there. So according to these ASTM standards, you can make a specimen that what are the size and all will be given. So according to those guidelines, you can make a specimen and you can perform the test in the laboratory itself. There is various tests you can make it, like how to find this E value and the G value and all. So according to that, you can make the specimen and you can perform the experiment. And from there, you can find various material properties called Young's modulus and shear modulus and even Poisson's ratios and all. Then those values, the same format now. Once you got that one epsilon and all, those you can substitute here. So in that case, procedure is same. Procedure way is same, but only the finding the E value and all will be a different one. That's all. Remaining all procedure is same. And you can compare with your experimental and the theoretical results also.
Yes,
that is
sir,
possible, sir.
Thank you, sir. Thank you.
But I am not very sure which sort of ASTM standard, but that you can refer from the literature.
Okay, sir. Thank you, sir. Thank you.
Yes. So that is a good area because most of the people have not done that area. Mostly they are fabricating and they are testing it. But nobody has done mathematical foundation. That is a good area. You can work it on it.
Thank you.
So we have a question in the chat.
Thank you, sir.
Yes.
Can we compare the solutions obtained from Matlab and ANSYS?
Yes, sir. You can compare. You can compare definitely. Paramassivam, sir. You can compare, sir. Femur bone structure analysis. How to do the mathematical modeling. bone structure, we have to see the structures, then only we can do it. For you mean to say that mathematical modeling perspective. Maybe you need to go for this advanced FEM technique. Then only you can do this femur bone things. Where the solid structures is there, those you have to consider, and then you can write a FEM itself, pure FEM. And their meshing also will be ANSYS meshing will be different, and all these things. Yeah, you can do that way, sir.
Any other questions? So I think no other questions.
Okay. Yeah, definitely. I'll share the PPTs.
Yes, sir. No. This session is available on YouTube, Dr. Himanshu sir. The link is shared in the group. You can always access that.